In this video, we will discuss dispersion. We will need to remember that the speed of light depends on the material. In vacuum, the speed of light is 299,792,458 meters per second. That is an exact number by definition. In fact, the length of the meter is defined so that the speed of light in vacuum is exactly this value. And in a material, the speed of light is smaller, and we have already introduced the index of refraction, n equals c over v, where v is the speed of light in the material. And we have already seen that the wavelength is also smaller in a material, and it is given by the wavelength in vacuum divided by the index of refraction. But in fact, it is more complicated than that, because the index of refraction n also depends on the wavelength in vacuum lambda naught. As you can see on this graph, the index of refraction in different materials goes down as the wavelength in vacuum increases. Right? So the index for violet or blue wavelengths is slightly larger than the index for red wavelengths. And so if the index is different, then according to Snell's law, if you have white light that arrives on a prism, the angle of refraction for each color will be different, and so each color will emerge with a different direction, and this looks like the rainbow's colors. In fact, rainbow is what it is. It's also physics 9b. You can see the series of colors from violet to red, and this is because of dispersion of light in droplets of water. Sometimes you can even see a secondary rainbow above the primary rainbow. And if you look carefully, you may notice that the colors of the secondary rainbow are inverted. They go from red to violet. And so to understand this, the first thing to understand is that most of the light that is reflected out of a droplet is not dispersed much. For the most part, the violet light and the red light are very much together, right? So we see them as white color. But if you look at the light that arrives on top of the droplet, it is reflected with the largest angle. It travels the largest distance in the droplet, and it has the largest dispersion. And by dispersion, I mean that the violet light and the red light are separated the most. And so in fact, the violet light emerges with an angle of 40.8 degrees, and the red light with an angle of 42.5 degrees. And so to summarize, most of the dispersed light is at the maximum angle, and the angle is larger for red colors than for violet colors. And so it will appear that violet and blue colors are coming from lower in the sky, and red colors are coming from higher in the sky. And so that gives the distribution of rainbow colors from violet to red. Now for the secondary rainbow, there is a second reflection inside the droplet, and this happens for a smaller fraction of light that arrives at the very bottom of the droplet. And the light is dispersed even more because it travels more distance in the droplet, and the red colors emerge at an angle of 50.1 degrees, and the violet colors at an angle of 53.1 degrees. And so for the secondary rainbow, the angle is larger for violet than for red. And so the colors are reversed compared to the primary rainbow. For the secondary rainbow, it will appear that blue-violet colors are coming from higher in the sky and red colors from lower in the sky.